we could begin while other people are joining in. Maybe we could commence with the introductions.
Okay.
Good. So good evening, ladies and gentlemen. Welcome to today's webinar on physics with Vernier. My name is Santosh. I represent Edutech India Private Limited. I'm dialing in from Chennai. I have with me Mr. Gerard Escura and Mr. Jake Hopkins. They are from Vernier, and we're all extremely delighted to have you attend this particular webinar. I'll invite both Gerard and Jake to give a brief introduction about themselves and the role that they do in Vernier. And we'll be beginning the session very shortly. We're expecting a few more educators to log in. So I thank you for your patience. Gerard, would you like to do the honors?
Good evening, everybody. Many of you know me already. My name is Gerard Escura. I've been managing the international customer base for Vernier for next year will be 25 years, so for a very, very long time. I've traveled and met many of you, and I look forward to a good webinar today. Hopefully we'll give you some new insights that you haven't heard before. Jake, off to you.
Okay, my name is Jake Hopkins. I am one of the physics specialists here at Vernier and in Beaverton, Oregon. I've been with the company for 22 years, and I'm one of the physics specialists. We wear a lot of hats, so I do many other things, including I started doing our webinars here in the U.S., and we found that this is a really great way to reach out to people that we find in the U.S. a lot of times in rural areas where it's more difficult to travel to, and we've more recently started using this internationally. So we find this a great way to do training. It is a little unusual because all of our technology is geared for hands-on, and this is more presentation style, but we talk about how to use it for hands-on. So I'll be taking questions throughout the webinar, but if you have any, if you'd like to send them in via chat, I'll be sure to collect them all at the end, and I'll circle back and answer any questions that come through. While I'm presenting, though, I probably won't be reading the chat because I can multitask a lot of things, but not all of them. And let's see, so what else? We'll be doing mostly physics today. As Santosh mentioned, we have two webinars this week, one in physics, one in chemistry, and the chemistry one will be on Thursday. So a little bit about what we'll be covering today, overall approach of using this kind of hands-on technology and some of the methods that we use when teaching it. Now, as far as choosing sensors today, my overlap of things that I know are in the International Baccalaureate curriculum, most popular physics sensors, what everyone mentioned in the pre-conference survey that they wanted to cover, and then also mix that in with some of my personal favorites. So that'll be more on the mechanics side of things. There were some questions around other topics. I can certainly cover some more of those if people have, especially if you have a sensor and you're not sure how to use it. I'm happy to go over some of both the lab ideas that are in the lab books, as well as some creative things we've seen teachers do with any individual sensors. So from the survey results, I know that there's a wide variety of people who are either just starting with probeware or have been using it for quite a while. So it's a lot like with a group of students. You have a wide range of skill levels and comfort level with the topic. So we'll sort of start from the beginning, and then I'll very quickly go through at least one semester worth of physics labs that you can cover. So one of the things I always like to talk about, though, is the benefits of using this in the first place. Of why would you go to the expense, the time, the effort to use this kind of technology in a classroom? So one of the biggest things is that in a study of different learning styles, we know that more people tend to visual, and whenever you have a visual to go with the topic that you're learning, it becomes more and more real to the students. Now, demonstrating to a group of students and having it on the whiteboard helps, but it's never quite as good as actually having a deeper, richer, hands-on experience. So there's the age-old expression of, I hear, I forget. I'm sorry. Sorry. A little technical issue there with WebEx. There's there's an old expression that is, I hear, I forget, I see, I remember, I do, I understand. And that's sort of the level of deeper experience that you get. Of if your students actually use this kind of technology hands-on in the classroom, they really do understand more in a deeper, richer way, and then also just for differentiated instruction. Your kinesthetic learners who need to be moving a little bit more can actually do that. The people who need to process auditory-wise can communicate with their lab partner. They can talk through the labs. And then also classic Socratic method of doing predictions and then analyzing what they're doing, drawing their own conclusions, not necessarily just say back what the teacher said to them. So it really is very useful, and it's like any other tool, though. It can be used in a lot of different ways. So depending on the class, the teacher, the method, the topics, it's very adaptable and can be useful in lots of different ways. So let's start with an experiment here. So one of the activities, if you don't know about this page, I end up referring back to the Vernier website quite a bit in my presentations. If you go to vernier.com/IB, we have a listing of the correlations between the IB physics curriculum and all the different lab books. So you can scroll through here and see basically the topics and the subtopics within the International Baccalaureate Standards, and then the labs and how they match up with the different Vernier lab books. So what I have connected here is, another one here, is I have two of our dual range force sensors connected to my computer. So this one will measure push and pull, and this is actually a photo of the lab that we're doing here, where you can use two students pushing and pulling to measure the forces in real time between the sensors. So I have two of them connected to my computer here, and we'll typically start with one. As you cycle through Newton's laws, it's always best to start from the least complicated and work your way towards the more complicated. Newton's third is one that we found that students struggle with a lot in traditional methods, but when you layer in probeware, they really it's really a great jumping off point for letting the kids experiment with every combination that they can think of for when is this. I know there's a trick to this. At some point, there's going to be more force on one than the other because they're just certain that is the truth. The big one has to push more than the small one. So I'm going to show you a little bit about how to set this up. And when we first connect it, if you're not familiar with some of the setup within Logger Pro, I've got two sensors connected here, and I get a live readout. They'll both be close to zero. And let me get some of my video controls out of the way here. If I choose to zero the sensors, it'll ask me when I have two, do I want to zero just one sensor or the other? And I'm going to leave both of those checked to say OK. And this is a bit like tearing a scale. It's just defining whatever the force that's applied on the sensor right now as zero. So I hit OK. And now that's going to go at or very, very close to zero for both of those two sensors. And if I just say collect, now remember, I haven't told Logger Pro yet which lab I'm doing. It just knows that there are two force sensors, so it's not really tuned to this specific activity yet. So if I hit collect, and what I'm going to do, I'm going to lay it on the table here, but I'm just going to hook the two hooks together and pull them apart. Now, when we give it to students, what we'll do is we'll attach it with a piece of string or a rubber band, something so that they can more easily vary the forces. But since I'm working from home this morning and I don't have the full physics lab and all the different apparatus, I went for the simpler setup of just having the two sensors connected directly with their hooks. So if I click collect, I'm immediately going to get a real-time graph. And notice here, so as I'm pulling these apart, I'm getting two traces, but they're perfectly, very closely anyway, overlaid with each other. So in this case, because I haven't told the software what I'm doing yet, it's defined in both cases. For the sensor, a pull is defined as positive. But for this, what we want is, because we know we're going to have the two sensors connected, what we really want to define is one or the other direction to be positive. So what I want to do is reverse the sign of one of the two sensors. And if I go in to my Logger Pro controls here, if I tap anywhere up here in the toolbar where I've got live readouts of the force sensor, I can choose one of the sensors, and one of the options in here is reverse direction. So without recalibrating or re-zeroing the sensor, it will now define, instead of pull being positive, it will now define push as being positive for one sensor and pull as being positive for the other sensor. So now, if I just do another run, and I do collect, now we can see something that's just, that although the science is exactly the same, because I'm now seeing equal and opposite, which at this point the students would have had a discussion about Newton's third laws, about equal and opposite forces. They can see that these two graphs are going to mirror each other. So as I'm moving back and forth, I'm always going to have an increase on one and a decrease on the other. And let's see, my camera's not being kind to me, so my desk isn't all that interesting anyway. But I'm literally just pulling these sensors apart as we go. And there are a lot of variations you can do on this. You can have the students literally stand as was shown in the picture there. This is from the advanced physics book. This is I don't remember the experiment number right now. But this is one of the ways that we do Newton's third law. And if we want the students to take a deeper look at this data, so I'm going to turn on the Examine tool in Logger Pro. So up here in the toolbar, if I choose Examine, as I move back and forth across the graph, and this is one of the things I really like about Logger Pro, is that the students are going to see the data presented in multiple formats at the same time. So for anyone new to Logger Pro, this tool that I turned on here, now as I move back and forth across the graph, my live readout is going to show the forces at any given time. It's going to show me at what time that I selected. And then notice also what's happening over here in the data table. So it's scrolling to the row that matches the time where I collected this data. So I can see at any given point, so at t equals 1.2 seconds, what my forces were. And over here in the table, I'm at 1.2 seconds, and I can see what the forces were. So I've truly got equal and opposite. So one of the other benefits of using the rubber band is you'll smooth out any of the little bumps and collisions, and your forces will match much more exactly than the lazy method that I used of just connecting the two hooks, because whenever they become decoupled, they're no longer truly a pair. So if there's a little bit of rattle in between the two sensors, the readings might get a little bit out of sync. But by having a rubber band between the two, we'll get smoother, more even forces. And you see that that's a good general tip with the force sensor. Anything you can do to make the part of the experiment when the forces are in contact to be slightly longer, even by tenths or even hundredths of a second longer, you'll get smoother data that's more reproducible. So I can also, if I want to look at changes here, so let me show a couple things here in the toolbar. So in this case, if I wanted to really look at it, I can integrate under the curve, and I'll integrate under both of these. And in this case, I'm off by a little bit. It's pretty close. So under my force 1, I had an integral there. So it just tells me the value of the shaded region under the curve. In this case, it was minus 2.6 newtons. And under the red one, I was also at 2.6. But I'm off by a few hundredths of a newton there. And I think if I'd been a little more careful, it would have come out even closer. But the idea of this is the shaded region under the graph, and in one, we're shading from the top down because we were above 0 because we reversed our coordinate system, and then from the other, we were shading from the bottom up because we had the opposite, equal and opposite forces. And I can do that. I can repeat that at different parts across the graph. So I could say, well, what about over here? Is it going to look the same? So I can get I can get a lot of things going on my graph here and compare multiple regions, kind of however I like. So. And in Logger Pro, if I want to turn off any of these, I just hit the little X in the corner, and I can turn off any of these floating tools if I want the students to focus on one given part. Now, it could be that I also wanted to maybe over here on the right side of the graph in that second half, things were not as interesting. If I want to focus the students on a given part of the graph, I can always, if you just draw a box around the area of the region of interest, in this case I'll just say, okay, maybe this interesting little squiggle here. If I draw a box around that and then choose zoom in, which is just the magnifying glass with the plus, what that does is crops the graph and zooms it into just the part that I want the students to focus on. So if, for example, I had a motion detector graph and maybe I had a few seconds of setup, and then the actual experiment occurred later, and then a few more seconds afterwards where things are not as interesting. A lot of times the students have trouble discerning what was the setup, what was the actual lab, and then what was the noise. What are the things we're not interested in? But if you can get them to look at, okay, let's talk about this part right here. Now there's less information for them to process, and you can focus on the phenomena. Things like if we were doing a ball drop with a motion detector, there'll invariably be some wait time at the beginning, and that's fine for the students to see it. But when you really want to get into the analysis, it's usually best to get them to focus on just one portion of the graph so that you can see what's happening a little more clearly. So the zoom in feature, even though it's very simple, is extremely useful for getting the students to focus and then go deeper on the part of the data where the lab is actually happening. So, and then as far as scale, there are other times when you might want to do this as well. So I could zoom out then, and if I just choose that once, it's going to go back to the default reading, where I could go out to ridiculous proportions. And if you're teaching lessons on scale, which there are some things in the IB curriculum about reading and interpreting graphs, deciding what's on the axis, what's an appropriate label. So right now, the data is the same, and you can actually you can confuse the students with this a little bit. And remember, confusion. This is one of my new favorite sayings. Confusion is the sweat of learning. If the students are scratching their heads and they're not sure what's going on, that's often a good thing, as long as you have them confused at the right points. So you can say, what happened to my data? And then let them discuss. Just show them this graph. And if they're observant, they'll notice that on the vertical axis now, instead of going plus or minus 10 newtons, I'm now at plus or minus over 1,000 newtons. And on the horizontal axis, instead of going from 0 to 10 seconds, I'm now at minus 600 to plus 600 seconds. So now I've got something that looks much more like a postage stamp in the middle of a soccer pitch. It's this tiny little thing on this great big scale. So, but did I fundamentally change the data? Is it still the same thing? So we could question that, and we could look at it numerically instead of graphically. Okay, wait, these didn't change, but this is the same. So And you can, that's always a good thing to do as far as just looking at the scale of the graph and does it pass the sniff test? Does it make sense? If I choose auto scale, if I do this and get into some crazy setup in my graph, I can always choose auto scale, and then it will choose a best guess for the horizontal and the vertical scale and zoom in on the graph. If I want a specific, I can always click on the axis label. Let me move this out of the way. So if I click on the largest number displayed, and it'll let me edit the endpoint. So if I wanted this to go to, say, 10, I can just type 10 there, and if I wanted to go to minus 10, I can say minus 10 here, and then I can manually just change the scale of the graph. Because it could be that on my next trial I'm expecting greater forces or whatever it may be. But the overall philosophy of Logger Pro is whenever you see something on the screen that you want to change, just go ahead and click on the thing that you want to change it. So that applies also to the horizontal scale. If I wanted this to go out longer for some reason, maybe to 20 seconds. Or if I wanted to set this to go maybe to something before 0, I can always just, and notice here I can click on either the minus 10 to set the vertical axis scale or the 0 to the horizontal axis scale. So I can also double click any of my live readout numbers here, and I can format, I can change the font.
Jake, Santosh here.
Yes.
Sorry, could you mute all the participants' mics, if you don't mind?
Sure, just a sec.
Yeah, there are some background noises coming in.
Sorry, let me switch back into. There we go. So I went ahead. It was fewer clicks. Mute all. Santosh, I believe you can unmute viewers. If you can't, hit me on chat, and I'll turn off the mute on yours. Sorry about that. So so I can change the scale. I can get the students to focus on specific portions that I want them to look at. And if you haven't seen some of the other things in the toolbar, there are Logger Pro is very deep and rich. I tell physics teachers a lot that we spent basically the last decade adding almost every feature that physics teachers want to Logger Pro. So there's a good chance that if there's something that you want Logger Pro to do, that it is already there. The things that are the most popular, that get used the most, we've added to the toolbar at the top. So these are the things that are used kind of day to day. There are many other options buried in the menus here in Logger Pro. So you can tell there's options within options. But the things that are the most common are up here in the toolbar. So let me just take a quick tour of these. So I can, as I mentioned earlier, if I wanted to zoom in on a given portion, if I highlight that, notice again, highlighted over here in the table, highlighted in the graph, I can zoom in and look at only that portion. And just as far as simplifying display, I'm going to leave it zoomed in here. So if I wanted to look at this particular part, I can again highlight this area, and my examine tool is already on. If I go back and forth, I can see what the forces were at any given time. I can X out of that and remove that. I can also, let me make this just a little bit bigger, and I'll make this so I can see the top here. So if I go into my tangent tool, now as I move back and forth across the graph, I'm seeing this black line drawn. I'll leave the examine and the tangent tool just for illustrative purposes here. I can now see a line that's being drawn at a tangent to the data. Now, when we work with people who teach math, we found that they really like this tangent tool because this is oftentimes a point where the math stops making sense for students. In the U.S., there's a growing number of physics classes that are now being taught at younger grades with less math in them, because we found that teaching physics at a higher level that requires more math means fewer students get physics. But in physics, this is an ongoing rivalry within the office and within the disciplines, which is the most pure science. And of course, there's no really good answer to that, but we all know that physics is one of the best. Is that because in physics we break things down into very simple components, and it's actually good for constructive understanding to be able to start with breaking things into very small, manageable chunks, and then building up in complexity from there. So in that way, physics actually is very good at looking at things that are very simple. And in this case, just looking at the simplicity of this graph. What is the change in the force right now? That's what's represented by that tangent line. And you know that, but your students, a lot of times when it's taught in a math context and there is no connection to the graph, and at any given point they might have to actually calculate the rise over the run, being able to see just, oh, we have this flat line that sort of surfs across the curvy line, and you can ask questions like, okay, why would it be, so we're looking only at the blue line right now, so typically we would do this with just one sensor for simplicity, but why would I have a positive number over here and a negative number over here? Just asking students that question and letting it hang in the air can lead to a very good discussion about what does this number actually mean? Why would it be negative over here versus positive over here? Because you'll find that even though a lot of your students are able to answer the question, what is the slope? Oh, it's the rise over the run. They can echo that back to you, but as far as actually understanding what it means, as far as rate of change, being able to really understand that and build that as a concept through in physics helps you understand the math of it, and then from there you can use that skill in many, many places. So anyway, I really, really like that tangent tool. And whenever you have anything that's sinusoidal, it's very just sort of a visually entertaining piece to look at. We've got a flat line that sort of surfs across the curvy line. It's a great way to get students started thinking about the math behind the science. So let's see. If I highlight my region here, I can also do a statistics tool. So I'm just going to choose my force 2, which is in blue, and it'll give me a quick statistical analysis of that data. So I can get the min, the max, the mean, the standard deviation, the total number of samples, and the delta y, how big is the box that I drew? Well, what was the total change in force represented by that area? And again, I can turn that off. And if I were to choose that without selecting a region first, if I just choose stats and I don't have a region selected, now I can get statistics for the entire run of the data. So I can see the stats for my entire set of data rather than just the portion that I've selected. The integral, if I highlight a region here, I can integrate under my curve, and I used that a little bit earlier, but and I can also, I should mention this, a lot of times people have used Logger Pro for years and not noticed that these little brackets are actually movable. So if I grab the bracket for my selected region, I can widen the area of the selection to change that. And I will turn off my integral tool again. And let's say I want to look at this whole region. I can choose a linear fit. In physics, of course, we like nice straight lines. It'll tell me the equation for that it drew here. So I used y equals mx plus b, where instead of x though, we have t for time. We get the value of the slope, the y-intercept, the correlation, basically how close to linear is this, and the root mean square error. So I close that. And then one of the things where the real power of Logger Pro comes in is if I want to apply a different curve fit. So in the curve fit dialog, I can look at all sorts of different options for what type of mathematical relationship might describe the relationship between force and time for this particular graph. So I can go through and look at quadratic, cubic, quartic, quintic, inverse square, natural log. I can try any number of these relationships and see what they look like as compared to the data that I actually have. I just select the equation, and then I can also manipulate individual variables to see what effect that has on the graph. So when I try it out, though, it'll take basically a best guess and try to fit that. Now, remember, the students can get something that might fit to the data, but not describe the actual relationship. So it's another great way, as far as the math-physics connection, is to really look at what mathematical model might be behind this, and you can even let the students define their own functions. So I'm going to cancel out of that, though. And let's see, if I wanted to customize my parameters here, I can also change the sampling rate, the duration, any of the particulars of how the data that I'm going to collect are collected. How fast, how long, is there triggering? I can configure this in lots of different ways. I can also set it to repeat after I run one set of samples. Sorry, we're getting a little bit of interference there. I'm going to go ahead and mute to cut back on the interference here. Okay, so those are the basics of what's up in the toolbar. And for formatting the graph, I'm going to turn off my examine tool. I can also do, again, that philosophy of if you see something that you want to change, just click on the thing that you want to change it. If I double click anywhere in the graph, I have lots of options for formatting this particular graph. So I can add labels. I can add a second a right y-axis. I could add a graph title. I could change colors. I can modify the background style, the density of the grid, the colors of the graph, just almost everything that you want to change about this graph. If I double click on the graph, I get all those options. In this case, I just added a graph title, something pretty simple. But then if I ever want to go back in and change that, again, just double click, and I could put whatever I like in any of those areas. And the same applies for the table. I could change the font sizes, colors, bold, italic. I can also apply it to specific columns. So clicking on the column header will do something that applies only to that particular column, whereas clicking on where cell 00 would apply to the entire graph. So I could remove whole columns or format the entire table. So lots of options there in Logger Pro. And the thing that I didn't show, though, was one of the things to make some of the setup less necessary. So if we go back to the IB correlations here, let's see. Newton's third law appears both in the Physics with Vernier lab book and the Advanced Physics with Vernier Mechanics lab book. There was a question that came in on chat about some of the lab books. If you don't have any of the lab books, these are extremely useful. So the Advanced Physics with Vernier Mechanics lab book came out a few years ago. This is where we get a little deeper into the mechanics. We do more of the advanced labs. This is typically for your more advanced students. The Physics with Vernier is designed. It was based around a sort of a standard high school physics curriculum in the U.S. And then this one goes deeper. It's used quite a bit in both IB and the advanced placement curriculum, and includes topics. It's all mechanics, all the kinematics experiments, but done at a higher level. So we have correlations between them and all the different the major curriculums that we support. The table of contents is, of course, listed on the website. It's also broken out by which sensors are used. So in this case, if you have a sensor and you're not sure how to use it, you can go to that lab books page, and it will give you it'll give you a list of labs from this particular book that use that sensor. So the one that I'm doing here is Newton's third. And if you don't have the lab books, one of the other nice things about these, so the website will give you, or sorry, I'm doing a modified version of this one. Sorry, not enough tea this morning. So in this one, this goes more into the impulse momentum and the collisions. So there was also a question about doing experiments on tracks. So for kinematics, the cart and track system is almost like a canvas where you can paint whatever you like on it. For almost anything in the mechanics portion, the track keeps everything nice and linear. There's lots of advantages to that. Everything will stay aligned. You can do nice smooth collisions. The motion detector can always see the cart. You can mount, in this case, we could have the force sensor mounted at the end of the cart. And what we use as a bumper, I mentioned earlier, if you can make the collision last a little longer, we have a hoop spring. It's literally just a band of metal that you might use for shrink wrapping a pallet for shipping. And we take a short section of that thin metal and we make that into a bumper. So I can show a better picture of that than I can do with my hands. So this bumper launcher kit is an extremely popular accessory. So this hoop spring connects on to the end of the force sensor, and then there's a pedagogical advantage of it looks like the bumper on a car. So the students think of it as more like the motion of the collision of the bumper on a car because they see it compress and then decompress during a collision. And for the sensor, it also makes that collision, instead of very brief, now they can see a cushion and a back out. They sort of perceive it as more like a collision between two cars, which is what they usually think of with collision. And then it comes with two different stiffnesses of springs. So you can have very repeatable results, and the sensors are also the bumpers are also very Hookian in response. So if you actually wanted to plot the response curve on them, it's extremely reproducible. So anyway, we use this bumper launcher kit, and it also comes with if you want to do elastic and inelastic collisions. So the inelastic little lumps of clay, springs, lots of things you can do for different flavors of a collision. So Impulse Momentum Lab, we look at force over time as a cart collides in with a stationary force sensor. Variations on that, of course, you can always put the force sensor on the cart and do cart-to-cart collisions. That's a great way to show Newton's third law of pairs. And then we'll also go into the impulse momentum, integrate into the curves, and you can look at what the impulse curve is like. So this lab, though, if for any reason you don't like the way that we do a lab, which is the way, this is one of the fun parts about working with teachers, is that people tend to be very creative. You also have the Microsoft Word files. So you can edit any of these labs to fit your own style. So in this case, this lab is written with the motion detector. There are other versions to use other sensors you might have, including the motion encoder, which is what the students in this photograph have, where it's reading the position optically on its position on the track rather than from the motion detector, which would read it ultrasonically. So we write different versions of the lab based on what experiments you might do. But then some universities will actually just take our procedure and put their own complete wrapper around that lab. They'll really only take the step-by-step portion of one part of the lab and then take it in a completely different direction by having a different introduction, different conclusion, asking the students different questions. You can modify it in every different way. The nice part is, though, if you do the lab as written, it works. You know that it works. These are all written by teachers, for teachers. What some people tell us is the first time they do a lab, if they're introducing it, if it's maybe the first time using this type of lab with sensors, they'll do the lab, the stock version, the first time, just to build confidence and know that it's reliable, repeatable, and everybody gets good results. And then the next time they do it, they'll make their modifications and start to make it more their own. And that's one of the fun parts about working with teachers, is just seeing how many different ways that people take given experiments and take them in different directions. So one of the other ones I was going to show with the force sensor is, let's see here. Actually, I guess I should pause for a moment. Santosh, do we have any questions by chat? Should I circle back and answer your questions now before I change gears and show some other questions?
There are some questions, but I think Gerard has answered most of them via the chat interface itself. But I think there's one from Nupur Hardikar who wants to know how the charge sensor works.
The charge sensor. Okay.
Yeah.
I can cover the charge sensor.
Then there is Mr. Vinayak Shinde who wants to know how does the colorimeter show only absorbance values up to 2? So that's the second question.
Okay. Let me do some of the other sensors here in a couple of minutes. Watching the time here, and let me just mention one other force sensor activity, and then I'll switch into some of the other labs here. So the let's see. In physics with Vernier, this is another popular lab with the force sensor. It's also just a sort of more of a good intro. I chose one of the more advanced ones to start with there, where we connect the force sensor onto a block, and then we can and we just have some added mass to it, and then we drag the wooden block across the table, and you can by changing the friction force, you can basically put a different piece of sandpaper under the block versus a piece of felt, or different surfaces to change the friction. And then the students can see, if you've ever done this with a spring scale, the spring scale is always oscillating a little bit. It's quite noisy. So for the students to know how much force did it take requires a judgment call, and that's not always all that simple. But if we do it with the sensor, we can report the average over a time, and then with much more confidence, they can say how much force was required to drag the block under a different set of conditions. But the interesting variation that we did on this is we actually had a version of this written for younger students, and now what we see is some of the high school teachers will start this with a block of wood, but then they want to make it more interesting. A block of wood is a very sort of generic example. So if you've ever done free body diagrams where instead of just having a block of something, you make it into a jetpack on the back of a turtle, or something just more interesting to get the students to pay attention. In this case, instead of just drawing something and making it more creative, you can replace that block of wood with lots of different objects you might drag across. And tennis shoes are a very big topic of interest. It's definitely one of the fashion pieces that the students pay attention to quite a bit in the U.S. So we'll do the coefficient of friction for different shoes. And if you take a tennis shoe versus a high-heeled women's shoe versus a slipper, and look at the friction forces, and you can talk about that in an interesting way, because if you do look at something like a dance shoe that's designed to be able to slide across a wood floor versus a basketball shoe that's designed to be able to stop very quickly, you can ask good questions about why might this be designed the way that it is. So doing connections like that to any sort of a sport is also always a good way to engage the students. So feel free to make your own variations on these and have fun with them, because there are a lot of directions you can go. So I promised I would circle back through and answer questions. Now, unfortunately, I don't have the full 80 plus sensors that we make here at home, but the charge sensor. So this one, oh, and I should also mention, if you go to any given sensors page on our website, the charge sensor is a good example where we've got not one but 3 videos on them. Most of the time there's one video that shows sort of the basics of a setup, and that will kind of show you step by step both a basic setup and then in some cases 1 or 2 more experiments that are popular to do with that lab. And in this case, and of course it's also got all the specifications, the manual, all of those things are all listed on there. And then it'll also tell you which of the lab books use that particular sensor. So in the Advanced Physics Beyond Mechanics, so in that one we cover topics outside of kinematics, including electrostatics. So most popular activity with the charge sensor. Oh, I thought this one was going to have a diagram, but it doesn't. So there's a couple of things you can do with this one, and let's get. The simplest experiment is to literally just take a piece of Scotch tape, and as you lift the tape, enough electrons are transferred that you can measure that charge. But this whole electrostatics kit includes several other things you might add for. So you can use different. There's silk, fur, rods of different composition. As you rub it, you can get a different charge, and then you can look at how it's inducing that charge. There's a Faraday pail and a Faraday cage that come in this electrostatics kit. So it's very, very sensitive because we're talking about not a whole lot of electrons being transferred. It is one of the more sensitive sensors to environmental conditions, because if you're in a very high humidity area, it's difficult for electrostatics to work well. We know that some schools in the U.S. have moved when they do the charge unit in the year, so that they do it in the winter when it's very dry and the heat is on. So the air in the room is much drier. They're much more likely to get good results with electrostatics. We recently had someone that was having a very difficult time, and what they found was that I believe that was in Myanmar. Gerard might remember one of our dealers was having difficulty with it. So what we had to do was actually turn up the air conditioning to get drier air. It wasn't necessarily that we needed to change the temperature, as that we needed to get as dry air as possible to be able to get good results with this. And then we can measure the charge over time, so charge will bleed off. And then you can also measure the charge of a plane, of the ball, different objects, and you can induce a charge on a sphere. So there are a lot of ways to induce a charge. Let's see, what else can I say about the charge sensor? Oh, and this is the other physics book that I forgot to mention, the Physics Exploration and Projects book. Any intro physics course, this one is geared more around projects. This is our newest physics book, and it's been very popular. If we want to do more project-based physics, this lab book is a different style than some of our other labs that are more guided. These are a little more project-based and a little more open-ended. So the Coulomb's law is the other activity. Still no diagram there. I thought we were going to have a diagram for this one. But in this one, we'll charge a sphere and look at the charge and discharge in electrostatics. So the videos are a great way to see those in more detail. I'm sorry I can't show those a little better right now. And Santosh, you said the other question was about the colorimeter. So Thursday's webinar, we'll be talking more about the chemistry-related sensors. I'm sorry, I'm getting a little bit of feedback here. There we go. Sorry, I'm not sure what's going on there. I don't know if everyone's hearing that or not. Give me 1 second here. One sec, let me fix. Okay, hopefully that feedback will go away. So the question was if the colorimeter will do both absorbance and transmittance, and the answer is yes. So this one will work by we shine a light through the sample, and then we measure the light that comes out the other side, and we can do both the absorbance and the transmittance depending on the context. I can ask. So I forgot to tell Santosh this. Because we wanted to go a little deeper in some of the content on Thursday, and I'm more of on the physics side of things. I've asked one of our chemists to help us out here. I'm sorry, I'm getting more feedback here. I'm having a hard time hearing. So Noose Hissam, who's one of our chemists, will be joining us on Thursday, on this Thursday, and we're going to talk about the spectrometer, and we can also go into a little more depth on. Let me pull up my list of chat participants here. And Santosh, we're approaching the end here, and I'm sorry, I've been talking and not reading the chat. So, have there been any other questions on chat that you want me to circle back to? Or Gerard? He said, Gerard, you were answering some of the chat questions.
I think there are no further questions on the chat window. Just check them. Maybe we could open the mics for everyone and ask them to voice their questions if they have any. So there's a question from Pushpa Janardhan. She wants to know, how do we calibrate sensors?
To recalibrate a sensor, sure. I'm going to go to just a single sensor. I'm going to disconnect one of my sensors, and then in Logger Pro, I'm going to say File New. If you ever get, a good tip, if you ever get lost in Logger Pro, just say File New, and then it will revert back to sort of a best guess for what type of experiment you might want to do. In this case, it set itself up for a 10-second graph of force versus time. And in the experiment that I did before, all I did was zero the sensor. But instead, if I want to calibrate it, if I tap where I've got the live readout of the force up in the toolbar, I can also get to it from the menus.
Paul?
But I tend to be more of a people thinker. If I go into the live, yes?
Sorry, there seems to be some, somebody's mic seems to be open and there's a lot of ambient noise coming in. So we're not really able to hear you.
Yeah, I can. Okay, there, I've muted. So, and Santosh, feel free to unmute yourself if you want to moderate other questions. So, to get into this again, I clicked into the live readout of the force, and then I've got a diagram basically of all the sensors that Logger Pro knows are connected to my LabQuest. And then when I click the picture of that sensor, I go into Calibrate. Now, when I calibrate a sensor, I generally need to know 2 points where I have a known value for the force. And with the force sensor, in this experiment, I'm going to use it horizontally. But if in your experiment you're using it vertically, you want to make sure that when you calibrate it, you're using it vertically. Now, calibrating the force sensor always has to be done vertically because it only measures force along the axis of where the hook is connected. So it's a one-dimensional sensor, and that's important to know. So if I were going to calibrate very carefully, and I were in a lab where I had lab equipment instead of my home office here, I would have this mounted on a ring stand. And if I go into the Calibrate tab and then choose Calibrate Now, what this dialog is laid out to do is, what are the 2 readings that I'm using for the calibration? So what I would do is have it mounted with no force on it and enter a value of 0 known force. So that's my calibrated value. I know that I'm not applying any force to it. I'm defining that as 0, and I say keep. And then what I would do is hang a mass of a known amount. Since I don't have my my actual calibrated masses, I'll empty my teacup, and let's imagine that I already know how much applied force my teacup is going to have, and I can hopefully hook that on there without dropping it. And if I know exactly already from a calibrated value how much force that is, while it's in that setting, I would enter that value, and let's say that's 4 newtons. I don't really know, but I'll choose keep. And now I have defined a 4 Newton force from my teacup as the new standard international unit for calibrating calibrating in newtons. So that calibration is now in use for this particular setting, for this sensor in this session only. If I choose File New in Logger Pro, that calibration is wiped out because the sensors also have the ability to store the calibration inside it. And if I were using something like a pH sensor where I might calibrate it once or twice a year, after performing that calibration, I would go to the calibration storage and choose Set Sensor Calibration. What that will do is write the calibration that I just very carefully did into the sensor's memory, and then if I take this sensor and I connect it to a different setup in a different on a different day, as soon as I plug it in, that calibration is going to be loaded instead of the stock one that was created when the sensor was brand new. And chances are it's going to be more accurate because I've been very careful about how I've calibrated. I'm going to go ahead and choose not to do that today because I don't think this teacup should be used for any sort of standard international units. But I can choose the Set Sensor Calibration. It will warn me or remind me that this calibration is going to be kept for a long period of time, and then I'll write it back to the sensor. So I'm going to go ahead and cancel that now. So for any given sensor, it follows the same basic premise. You need to be able to provide the sensor with 2 known settings. And typically, if we can have one that's 0 and one that's a known value, that's the simplest. The force sensor is actually one of the easier sensors to calibrate. Things like the oxygen gas sensor, we need to make sure that we have a button on it to basically to cut the signal so that we can define it as 0 on the input. So you can calibrate most sensors in the same way with just a simple 2-point calibration. And Santosh, other questions? And I may have muted you. Sorry. I can open it. And I wanted to ask if there are any other questions. So I've opened up the mic so that we can hear from everyone. And if anyone has any questions, I'm happy to stay on the line here for a few more minutes. We're at the end of our scheduled time. Thank you very much for staying after school with us today. Appreciate everyone's there were a lot of good questions there, covered a lot of ground, and hope to see you again.